Hello, my name's Chloe and today I'm going to be talking about our paper Coevolutionary Learning of Neuromodulated Controllers for Multi-Stage and Gamified Tasks. And this work has been a collaboration between Aston University in the UK and the University of Oslo in Norway. As computer science researchers, we're often inspired by things that we observe in nature, and this has led to the creation of things like swarm intelligence and neural networks. But artificial and natural systems alike often find it difficult and also find themselves in dynamic and novel and uncertain environments. And neural networks in particular often struggle in these types of situations because they suffer from something called catastrophic forgetting. So when they try to learn something new, they have to change what's already been encoded within the network, and that can lead to a loss of information and a change in behavior. One way that animals overcome these difficulties is to show plasticity. So they can change their phenotype and their observable characteristics like appearance and behavior, depending on the environment that they're in. And we're going to focus on a specific type of phenotypic plasticity called behavioural plasticity. And this is where behavioural changes that are temporary and reversible can be made in response to changes within the environment. In nature, plasticity can arise as a result of neuromodulation, and this is a biological process that can be found in animal brains, and this is where a chemical signal can change or modify or regulate synaptic activity in the brain. And we hypothesize that as behavioural plasticity can be useful for animals to operate and achieve their goals in dynamic and uncertain environments, that this can also help artificial agents and neural controllers to do the same thing. In nature, the effects of neuromodulation are greater and more beneficial as environmental variability increases. And we therefore look at how agents can achieve their goals in environments that have different environmental variabilities in our work. And the overarching question of this work then is how can we design adaptive systems that express behavioural plasticity using neuromodulation to help artificial agents achieve their goals in dynamic environments. So to look at this, we use a testbed called the River Crossing Dilemma, and this is a 19 by 19 2D grid world environment with a river of water running down the middle. And our agents' goals are pretty simple. What they have to do is they have to learn how to pick up one of their allocated resources from either side of the river. So we've got two agents here, we've got one in grey and one in black, and they've got their allocated resources in the same colour. But the difficulty here though is that if the agent goes into the river, it's going to drown. So it has to learn how to build a bridge with two stones. So it places one stone in the river, finds another one, picks it up and puts that in the river as well. An added complexity of this environment is that it's also gamified, so there's an increasing cost of putting these stones in the river. And one thing to note is that cooperation and competition can emerge, but it can never be intended by the agents because they've got no idea of the existence of any other agents within the environment. And because we want to explore environments with different variability, we've created a multi-stage and a single-stage version of this task. So what I've described is a multi-stage task because agents must first and foremost learn not to go in the river because it's dangerous, and if they do, they're going to drown. So that's what they've got to learn first of all. But then they have to learn that the river's safe, but only when they're carrying a stone. So you have to learn this same behavior in different contexts. We've also created a single stage version of this task called the Protected River Crossing Dilemma. And this is essentially where the river basically acts like a wall. So the agents can't actually go into it and drown. So they never have to learn to not go into it. So it's a simpler task all round really. So how are our agents designed then? Well, we have two different neural networks. The first is called the deliberative layer, and this is where we take the state of the agent in as inputs. So whether it's on grass, a resource, water, a stone, whether it's carrying a stone currently, or whether a bridge partially exists in the environment somewhere at that time step. And this generates sub-goals as the outputs. So it decides what it wants to be attracted to or wants to avoid in the environment at that time step, depending on its state and the state of the environment. And our agents learn using something called neuroevolution, which is where we evolve the weight of this deliberative neural network over a number of generations by small mutations. So we change the weights incrementally over time. These subgoals are passed on to the reactive layer, and this is what the agent uses to hill climb and to decide what move it wants to take next. So there's a visualization of this environment in the bottom right-hand corner. So if an agent wants to go towards a stone, for example, it's going to choose the cell next to it with the highest value in order to climb that peak and to get to where it wants to go. Agents also have no prior knowledge about its task or the environment as well. So that's one thing to consider when creating and setting up this environment. So how do we incorporate neuromodulation into our agents then? Well, we have two different types of neurons. We have our standard neuron, which every neural network has, and we also introduce a modulatory neuron as well, which are the grey neurons that you can see here. And unlike other work using neuromodulation, we have the neuromodulation existing within the deliberative neural networks. We have it happening within one neural network instead of in a separate neural network. So what happens here is if positive activity goes through a modulatory neuron, it acts as a standard neuron. Nothing changes and it acts as normal. But how we regulate behavior and change the behavior temporarily of our agents is when negative activity comes into the modulatory neuron, the outgoing signals are modulated or gated. And this effectively means that the outgoing signal is turned off because we send a 0 as the outgoing signal. And this is how we temporarily change the behavior of our agents, because depending on the environmental stimuli, the inputs to the network, the output will be different depending on that input. So how are our experiments designed then? Because we want to explore what happens to our agents in environments with different levels of variability, we've got a set of 4 experiments. So we've got our single and our multi-stage task, and we also explore what happens when there's 1 and 2 agents in an environment as well. And when there's 2 agents in an environment, the variability of the environment increases because the actions of one agent will change the environment to be dynamic for the other agent. So we've got 4 different environments, 4 different tasks, 4 different types of experiment. And we can see very clearly that in each of these 4 experiments, the effect of neuromodulation is very beneficial in each case. And it's worth noting that the fitness for the experiments where there are 2 agents in the environment is higher than when there's 1 agent in the environment. And that's because the agents, when there are 2 agents in the environment, can access a higher fitness by exploiting or cooperating with the other agent in the environment. And that means that they're sharing the cost of building the bridge and therefore getting a higher fitness because of that. So let's dig into this a little bit more then. So with our single stage task, we can see very clearly that neuromodulation has a clear benefit in both instances, but there is a bigger benefit when there is more variability in the environment. So the benefit increases when there are 2 agents in the environment compared to just 1 agent in the environment. So there are 97% of the agents can actually achieve their goal when they use neuromodulation, when there's 2 agents in the single stage task, compared to just 61% of agents when they don't use neuromodulation. So that's a really big benefit there. So let's go ahead and look at the multi-stage task. The results are pretty similar, but they're slightly different because the task is harder than the single stage task. And this means that the agents actually take a little bit longer at the start of evolution to learn how to achieve the task because it's a little bit more difficult. But we can still see that the benefit increases when there are 2 agents in the environment. Looking at the stats, when there are 2 agents that use neuromodulation in the multi-stage task, 94% of them can actually achieve their goal, compared to 68% of the agents that don't use neuromodulation. So again, there's a really big benefit to using neuromodulation in this scenario. We've also conducted a fifth experiment as well, which increases the environmental variability of our environment further. So what we have here is we have an agent that exists alone for 500,000 generations, the same term period as before, but then we change the variability by introducing another agent into that environment. So we wanted to see how agents cope with that change in environmental variability halfway through. And we can see that with neuromodulation, the agents can actually combat that change in environmental variability a lot better than those that don't use neuromodulation. And this is so much so that when agents use neuromodulation in this environment, only one actually fails to achieve its goal. And that's compared to 27 when they don't use neuromodulation. So that benefit is very clear in this environment. So what are the implications then of this work? In nature, we observe that the benefit of neuromodulation increases with environmental variability. And we've seen that in our work as well. So the final experiment I just showed, where the variability changes partway through, that's where we see the biggest increase in benefit. And we've also explored what happened when we use a single or a multi-stage task, and what happens when there's one or two agents in the environment as well. And this proves that neuromodulation has a good benefit throughout all of these different types of experiments. And the takeaway from this talk is that adaptive systems can benefit from temporary and reversible behavioural changes to navigate and succeed in novel environments as a result of using neuromodulation. And that's it. Thank you very much for listening, and I'll be happy to take any questions that you might have.